So in the past, tandem-bladed inducers have produced higher head compared to typical flat plate inducers, such as the one described in this NASA technical note. And they also tried different clocking options and saw that the maximum head rise was achieved when the exducer blade was clocked in the direction of rotation. Now we have already seen that tandem inducers can be quickly generated in Turbo Design 1 by taking the original inducer and then specifying a particular loading and meridional split between the inducer and exducer blades. And since the blade surface minimum pressure is one of the performance parameters that we get from the inverse design solver, we can naturally use this to perform a fast DOE to determine the best meridional and loading split between the inducer and exducer blades for optimum cavitation behavior. So here is the DOE procedure where we generate different tandem designs by gradually increasing the inducer meridional length and correspondingly reducing the exducer meridional length, and also by gradually increasing the inducer work and correspondingly reducing the exducer work. Now for each tandem design, we note the global minimum pressure on the inducer and exducer blades combined, and then create a table of minimum pressures for all the tandem designs. And from this, it's very straightforward to pick the design with the highest minimum pressure, which is 70% meridional length and 60% loading on the inducer in this case. And these static pressure plots from Turbo Design 1 clearly show that the minimum pressure is more than the vapor pressure, removing the possibility of cavitation in this design. And so we use this as the final design for the tandem turbopump configuration. In contrast, we can also see that a 50-50 split for the meridional length and loading is not necessarily the best option, since the minimum pressure goes below the vapor pressure in this case.